Okay, so this is discrete optimization, constraint programming. Okay, so this is about global constraints. So what we're going to do today is essentially give you the basic intuition on how to implement global constraints, and we'll consider two of them, knapsack and alldifferent. Now you have to understand that this is a huge area of research. There are about more than 100 global constraints which have been defined so far. So this is only just touching upon the topic, but you'll get a sense of what it means to implement a global constraints in a constraint programming system. Okay, so the golden standard for pruning, this is the most important thing that we need to cover first, is that after the pruning, what we want to have is that for every value in the domain of the variable x, that is left in the domain, so that value is still in the domain of variable x. We want to be sure that we can find values in the domain of the other variables in the constraint such that there is a feasible solution for that constraint. Okay, so in a sense, you know that every value for every variable, is part of a solution to that constraint. So that's the golden standard. Now, historically, there are many names for that particular golden standard. Our consistency, domain consistency, we don't worry about those. We know that we have this golden standard that we want to achieve. Okay? In a sense, that golden standard is basically capturing what it means to prune optimally if you only have the domains. Okay, so if you have only the domains and the constraint, there is no way you can actually have a better pruning. So this is the notion of optimality that we have here. Of course, in practice, it may not be possible to implement this global standard in polynomial time. So if that's the case, we'll have to relax the standards and do incomplete pruning, or we'll have to settle for exponential time. Okay. So let me start with the binary knapsack, which is an example that we have seen. Okay, so the constraints that we have, you see it over there. We have a sum of the wk xk. Xk are decision variables, taking value between 0 and 1. And we want essentially this big sum to be between L and U. Okay? And so this is an example that I'm going to show you here, okay? And we're going to use later on in the lecture. You see the sum of the variable x1 and x2 and so on, and they have to be between 10 and 12, okay? And so the first thing that we have to do, right, because there are these two things that the constraint is to do, is feasibility and then pruning. So the first thing is to find out if this constraint is feasible, and then we have to see if we can remove some of the values of the domain of the variables, okay? Now, to find out if this is feasible, this is reasonably easy. I'm sure you can see it yourself. You give a 1 to these, x2, x3, and x4, and you have a value of 12. This is between the bounds, so you're happy this constraint is feasible. Okay? Now, the more interesting question here is that can you actually remove some values from the domain of these variables? In other words, is there a variable which cannot take the value 0? Or is there a variable that cannot take the value 1? Okay? So think about it. Okay? Can you see it? There is something to see here. Okay? So if you don't see it, don't worry. The algorithm is going to show it exactly what can be pruned in this particular example. Okay, so the basic algorithm that we are going to use for feasibility is based on dynamic programming. It's going to be pseudo-polynomial time. So if the numbers are small, it's basically polynomial time. If the numbers are big, then the algorithm is going to take more time. The pruning algorithm is interesting because essentially what it's doing is using the dynamic programming table to prune the search, to prune the domain of the variables. Okay? And so the way to think about this is that we'll have two phases. The forward phase is going to compute essentially feasibility and this dependency graph. How do we get to those values? Okay? And then we'll have a backward phases which basically remove some of the things that we don't need, and then it's going to basically show to you what values we have to prune. It's going to be beautiful. You'll see the pictures, and then you'll see essentially what you can prune and what you cannot prune. So in a sense, when we'll talk about the algorithm here, essentially it will basically combine feasibility and pruning in one algorithm. Okay, so this is the pictures that we are going to use. So what we see here are the value from 0 to 12. Okay, that's all the values that we will consider. Okay, and these big circles that you see there, basically we're going to see if we can actually get there. Okay, so initially what you have is that you have the set of all the values that you can get without actually picking any of the variables, without looking at the variables. And then these are basically the values that you can reach by taking a value for x1, and then you will do the same for x2, x3, and x4. Okay, and then essentially at the end you will see which values you can actually reach. Okay, so that's what we're going to do. Okay, so when we start, of course, if we don't use x1 or x2 or x3 or x4, the only value that we can get is 0. Okay, so we start from 0. That's the only value that we have at the beginning. Then we look at x1, and of course we can decide to take x1, or not to take x1, right? So and if we take x1, okay, so the value of its weight is 2, okay? So we can reach 2, and if we don't take x1, of course we stay at 0. And that's what you see there. You see these two arrows, okay? So one is going up, okay? That's the arrow when we pick up x1, when x1 is equal to 1, and we reach 2. And otherwise we stay at 0. And you see that we use two different shapes for these arrows. One is, a dashed line, the other one is a solid line, and you'll see why this is important later on, okay? Now we do the same for x2, and we can reach 5 values now, 0, 2, 3, and 5. 4 values, 0, 2, 3, and 5. And then we do the same thing for x3, and then we reach many more values. And then we do the same for x4, and these are all the values that we can reach, all the combination of 0 and 1 for x1, x2, x3, and x4. And that gives us the value which are basically between 0 and 12, except 1. We can reach everything. Okay? So that's basically the end of the forward phase. At this point, we have all these paths which correspond to taking some values for the variables and giving us a value for the sum at the end. Okay? Now the backward phase is going to start. And one of the things that we know is that this constraint to be feasible, we have to be between essentially 10 and 12. Okay? So all the other values which are at the bottom here, we really don't care. So we can get rid of them. Okay, and we can get rid of the nice arrows that were produced, because they are basically useless for us. They are not giving us feasible solutions. Okay, now we did that for x4, we do that for x3 now, and then we do that for x2, and then now we have this beautiful graph, okay, where essentially these are describing the path that you can take for the various variables, and therefore the combination of 0 and 1 for the various variables to arrive to a feasible solution. Okay, so we clean up the mess, such that we have only blue values for the various, transition states where for the various variables, and we have these beautiful things here where we see some arrows going, some dash arrows and some, solid arrows that in this particular graph. Okay, now there is something beautiful to see now. Okay, so if you look at a variable like, let's say, x2 over there, you can see that there are two, solid line and one dash line. What that basically means is that that variable can take the value 0 and the value 1. Okay, because the dash line is value 0, the solid lines are value 1s. Okay, now when you look at x4, that's very interesting. The only thing that you see for x4 are basically solid lines, and that basically means that value x4 cannot take the value 0 and produce a feasible solution. And that essentially tells us that the value 0 can be pruned from the domain of x4, and therefore x4 have to be 1. If for one particular variables all the lines were dashed lines, you would know that that particular value should be the only thing that variable can take is the value 0 and not the value 1. Okay, so now at this point you know everything. Okay, so you know how to prune and you know how to check feasibility. Feasibility is easy. You compute the forward phases. You see if you get into the feasible region. If you can't get into the feasible region, you are not feasible. And then essentially at the end, you prune with the backward phase all these dependencies, and then you look at every variable and see what kind of arrows you have, and that basically decides whether you can prune the value or not. Beautiful and simple, right? So that was basically the knapsack. What we're going to do now is to look at the all different constraints, which is also very interesting. The algorithm is going to be based on graph theory, and this is another set, and this exemplifies essentially another set of constraints heavily based on graph theory. Okay, so the feasibility here, once again, is going to be for every variable and every value, can I find values in the domain of the other variables such that all the variables get different values. Okay, and the pruning is that once again you're going to look at a variable, you're going to look at a value, and then you're going to say, can that variable can take the value, assuming that I have I can take values for the other variables. Okay, so this is, for instance, a simple illustration of the all different constraints. You see the variable, x1, x2, x3, x4, and 5, and you see the domain of every one of these variables. Okay, they take different values in this particular case. Now the kind of questions that we want to answer is, if all these variables have to take a different values, can x4 take the value too? Okay, so look at this. Can I find a solution to assigning values in the domain to every one of these variables such that x4 takes the value too? Okay, no, that's not obvious, right? And you will see that essentially x4 cannot take the value 2. There are no solution if you assign the value to x4. And so the algorithm is going to find that. Okay, there are other values that you can actually remove here. and this is a good question. Can you find the values that you can remove here? Okay. Once again, what we want to do is find those values efficiently and remove them from the search space. Okay, so to do that, we are going to use a nice representation. You're going to see the variables on the top. You're going to see the values on the bottom. Okay, and so in a sense, we're going to have two kinds of nodes. We're going to have the nodes for the variables and the node for the values. Okay, so these are the nodes for the values. You see value 1, value 2, value 3, and so on. You see the set, and then essentially, if a variable can take a value, we are going to draw an edge between that variables and the value. So when you see x1 over there, x1 can take the value 1, x1 can take the value 2. Okay. Now we look at variable 2. Variable 2 can take value 2 and 3. So we're going to put an edge from x2 to 2 and an edge from x2 to 3. And we do that for all the variables. And then you get this beautiful graph now where there is an edge between a variable and a value if essentially the value is in the domain of the variable. Okay. Now so far we haven't done very much except drawing a very nice picture. Okay, and once again, when with this representation, can you see that x4 cannot take the value 2? Okay, now so the first thing that we have to do is to find out if this constraint is feasible. Okay, that's always the first step. We have a constraint, we have a set of domain for the variable. Can we find a feasible solution? Okay. So what you see here, this is a feasible solution. Okay? So you see that the variable x1 here is assigned to value 1. You see that the variable x2 is assigned to the value 2, and so on. What is nice here is that you see this blue arrow representing the solutions. Okay, blue arrows. We're going to do that over and over again in this lecture. Okay? But essentially what we want is that every one of the variables on the top, I assign a blue edge. Okay? That means that they have assigned a value. And when you look at the values at the bottom, we want at most one of the blue arrows to come to them, because if there would be two arrows, that basically means that two variables are assigned to the same value, and therefore they are not different, right? Okay, so that's basically the idea. Okay, so it's going to be feasible if you have an arrow going from top to the bottom, and then there is one going from one, leaving every variable, and at most one arriving at every one of the values. Okay. So this is a feasible solution, for instance. Okay, so what we did here was just creating a bipartite graph. So a bipartite graph is a graph with two types of vertices, and the edges are between vertices of different types. Okay, in the particular case of the all different constraints, you have one type of vertices, the top ones, which are the variables, and then we have the bottom ones, which are the values, and there is an edge between a variable and a value if the value is in the domain of the variable. That's what we have done so far. Okay, so in a sense, you see this is the first set in the bipartite graph. That's the variable. You see the set of the values at the bottom. Okay, and once again, you have an edge between a variable and a value if that value is in the domain of the variable. Okay, now what we just did when I show you a solution was finding a matching. What is a matching? That's a basic concept in graph theory. And if you have a graph, with a set of vertices V and a set of edges E, okay, so a matching is going to be a set of edge E such that no two edges in E are sharing a vertex. Okay, so if you select an edge, you can never select another edge which is basically using one of the vertices of that edge. Okay, and then the maximum matching is going to be a matching where you have where you have selected the largest number of edges inside E. Okay, and so the constraint, of course, is as soon as you select an edge, you select two vertices, and these vertices cannot be selected any other edges. So you have to select these edges carefully. Okay. And so why is this interesting? Because essentially feasibility is basically feasibility amounts to finding the maximum matching. If you find the maximum matching, there are two cases, right? One of the cases is that the maximum matching as a size which is equal to the number of variables. That basically means that all the variables have been assigned, and by definition of a matching, they are assigned at different values. Okay, and at that point that the constraint is feasible. If the maximum matching is smaller than the number of variables, okay, that basically means that there is no feasible solution. There is one or more variables that I cannot assign. I would have to assign a value which is already taken by another variable. Okay, so in a sense, what I'm telling you is feasibility here equals matching. Okay, so now we have basically, this is an example. Okay, so you see, once again, the variable, the value at the top. You see these blue edges, beautiful. There is one edge leaving every variable. At most one edge arriving at every values, and you know that this constraint is feasible. This is another example. Okay, so you see this is essentially, once again, the variable, the value. This is a different set of domains here. Okay, and I can try to find a maximum matching, and this is what I get. At this point, what you see is this matching has only 5 edges, and I have 6 variables, so you know that the constraint is infeasible. Okay? So when you look at the variable x3 over there, you can see that I can't match any of these edges. I cannot use any of these edges because the values there are already taken. Okay? So essentially, the maximum matching here is of size 5. I have 6 variables. The constraint is not feasible. Okay? So essentially, now I know that if I can find a maximum matching, I will be able to decide if the constraint is feasible or not. Okay? So how do I find this beautiful matching? Okay? So I start with any matching, and then I'm going to try to improve them. Okay? So, and when no improvement is going to be possible, that basically means that I have a maximum matching. So it's a simple improvement algorithm. I start from any matching, maybe a matching with nothing in it, and then I improve it, and when I'm stuck, I can't improve it. I know that I have a feasible matching. Of course, I haven't defined what it means to improve a matching, but I'm going to do that in the next slides. Okay? So here, this is a matching. Okay? So you see that the variable x3, x4, x5, and x6 are basically matched. The variable x1 and x2 are not. Okay? So what I want to do now is improve this matching. Okay? So I can essentially replace the edges x4, which is assigned to 2, and the edge x2 to 2. Okay? I can replace the edge x4 2 by the edges x2 to 2 and x4 to 4. Okay? If I do that, I remove one edge and I add 2 new edges. Okay? And what I get is a better matching. Now 5 of the variables are matched. Okay? I can keep on improving this matching. Okay? I can essentially replace the edge x3 is assigned to 1 by 3 new edges. Okay? Actually, I have also to remove x5 to 3, and I replace them by x1, 1, x3, 3, and x5, 5. Okay, so I remove 2 edges, and I replace them by 3 new 1, and then I get this beautiful matching now, where essentially all the variables are matched. I have a maximum matching, and I will know that this constraint is feasible. So what I basically did was always selecting 1 edge and replacing it by 2, or selecting 2 edges and replacing by 3, and that's how I improve the matching. Okay? Now this is not precise enough, and I'm going to go into more details now. Okay? So once again, what we're going to do, start with any matching, improve the matching. How do we improve a matching? Okay, so what we will do is find a free vertex, and that will mean, in the particular case of the alldifferent, finding a variable which is not assigned a value. Okay? And now there are 2 cases. Okay? The first case is the case where I can find a value which is unmatched. That basically means that that value is free, no other variable is assigned to that value. If I can do that, obviously I can improve the matching. Okay? And I can put that edge in the matching and then start again trying to continue improving that matching. Now, the more interesting case is when that variable cannot be assigned to any other values at this point because all these values are taken. Okay? So what I do in that case is that I take that value, I assign it to the particular variable. Now I take the variable which is currently assigned to that value, I remove the edge between them, and then I start again with that variable. Okay? And I try to find an assignment for that variable to a value in the same way as I did for the original free variable. Okay? Let me illustrate that. Okay? So we have once again this beautiful matching with only 4 variables assigned. Okay? I'm trying to see how I can improve it. So I select the variable x2, which is free, and the value 2. Okay? So this is what you see there. You see the variable x2, it's free, no value, it has no value assigned to it. I take the value 2, but the value 2 you can see is assigned to the variable x4. Therefore, what I have to do is essentially remove the edge between x4 and 2, okay, and start again with the variable x4. Okay, so I remove x2 to 2, okay, and then I consider variable x4 at this point. Okay, and so I start again. So you see the variable x4 now is free. Okay, and I look if I can find a value for that particular variable. Okay, such that I can improve the matching. Okay, what is nice in this particular case is that I can assign the value x4 to the value 4. Okay, and therefore I have an improved matching. So what I did was essentially adding 2 edges, one from x2 to 2, and one from x4 to 4, and I remove only one edge, the edge x4 to 2, which was in the matching before. So I remove one edge from the matching, I added 2 new edges which were not in the matching, so I improve my matching. Okay? So that's the basic idea. So essentially what I'm using here is what is called an alternating path, okay? So if I have a matching, an alternating path from a free vertex in X, the top set of vertices, to a vertex in V, okay, that's the set of value, is going to be a path, essentially from this variable X to the variable V, where the edges are going to alternate between being not in the matching and being in the matching. So I'm going to start from X, take an edge which is not in the matching, go back to the top with an edge which is in the matching, and go to the bottom with an edge which is not in the matching, and so on. Okay? Until I find I can assign that particular variable to a value which is not taken by any other vertices. Okay? Now there is an odd number of edges here. Why? Because I start from the top and I end up at the bottom. Okay? So to go from the top to the bottom, I need one edge. Every time I go up and down, this is an even number of edges. So basically I will have an odd number of edges. And this is really important, right? Because if I have an odd number of edges, and I always start by taking something which is not in the matching, I know that I will increase the number of edges inside the matching by 1. Okay? So I'm improving essentially the matching. Okay, I remove, let's say, k edge which are inside the matching, and I add k plus 1 edges which are not in the matching. Really good. Okay, so these alternating paths essentially are allowing me to improve the matching. Okay, so how do I find this alternating path? You can see that I'm basically moving step by step, refining this concept one at a time. And this is the final step. Okay, so I'm basically telling you what the algorithm is. You have to create a directed graph, okay, given a particular matching. Okay. Now the edge of the matching are going to be oriented from the bottom to the top. Okay. So these edges are going to allow me to go to the top, and the edges which are not in the matching are going to be oriented from the top to the bottom. I'm basically will be able to assign a value to a particular variable. Okay, so this is essentially the illustration for the examples that you have seen. So you see these blue edges now, they are oriented to the top. Okay, and the other edges, the edges which are not in the matching, are oriented from the top to the bottom. Now I have a directed graph, right? And remember, what I want to do is to find a path from a free vertex to another free vertex on the top to a free vertex at the bottom. So when I'm going to go down, I have to take an edge which is going down, and those edges are basically not in the matching. And then I can only go up with edges which are in the matching. So I'm going to go down, up, on, up, not in the matching, in the matching, not in the matching, in the matching. And now I can follow the direction of these edges. Okay? So essentially, this is what I have done. Okay, so I create a directed graph. I take the edges which are in the matching, are oriented from the bottom to the top. Okay, and the other edges are oriented from the top to the bottom. And now essentially an alternating path is starting at the top and following these oriented edges until it reaches a free vertex at the bottom. Okay, I start at the top in a free vertex. I'm following these directed edges until I reach a free vertex at the bottom, and then I'm happy. Okay, I can find an alternating path, and therefore I can improve my matching. Okay, so look at this. Okay, so this is again a beautiful graph, oriented, and then I'm basically highlighting the vertex which are free at this point. You can see that x1 and x2 are free. At the level of the values, you have 4, 5, and 7 which are free. Okay, so what do? I start from something which is free, and then I try to follow a path until I get to something which is free at the bottom. Okay, so this is one of these beautiful paths, right? So you start from x2, you go to value 3, and then you go up to variable x5, and then you go down to value 4. Okay, so once again, it's nice. You start at the top, you go to the bottom with an edge which is not in the matching, take an edge which is in the matching to go back up, and then go down again. Okay, and now I can replace these things by the edges which are in the matching are going up, the edges which are not in the matching are going down. Okay, and now I have one more variable which has been assigned, and I have only one free variable here, which is the little x1 which is left alone. Okay, so now what I do is that I look at this guy, I try to find an alternating path from x1, and you're going to see it's a beautiful path going up and down until it reaches the value 5. Okay, once again, the edges we were going down are going to go up, the edges we were going up are going to go down, and this is my graph at the end. Okay, and now x1 has been assigned. All the values at the top now are assigned, and almost all the values are assigned, but we don't really care about the values because we really care about the variables and be sure that they are assigned different values. Okay, and at this point, of course, I have a feasible solution, and this is the matching essentially that I have. Okay? So this is essentially what I do, okay? So for finding alternating path, okay, I'm basically going from top to the bottom and until I get to a free vertex at the bottom, which is the free values. And essentially what I do is that I do that iteratively. I take a variable, I look for this path. If I can improve, great, I have a better matching. I take another one, I do the same thing. Okay, how do I find this path? I can use traditional depth first search or best first search to do that, and I get a very low polynomial algorithm to do that. Okay, so this is beautiful because now essentially I know how to find a maximal matching. It's a very simple thing. Okay, you just have to orient the graph. You have just to construct this bipartite graph, orient it in the right way, and search for the alternating path inside this directed graph. So to summarize, what we do is we build this bipartite graph. We have a vertex set for the variable on top. Okay, we have another set of vertices for the values at the bottom, and we have an edge between a variable and a value if that value is in the domain of the variable. Okay, then essentially the feasibility. Okay, so the constraint is going to be feasible if we have a maximum matching whose values is the same as the number of variables. And to do that, the only thing that we have to do is find these alternating paths, which are going to improve the matching one step at a time until we get the maximum matching. And when we have it, we just compare to the number of variables. Okay? So we have done part one, which is essentially finding feasibility. Okay? Now we have to prune now. What does it mean to prune? Is that if a variable x can take a value v, we have to see if that particular variable, belongs to a solution. That means that we can find values for the domain of the other variables, okay, such that all the variables are given different values. Okay? Now, if we translate that in the context of the matching, what it means is that this edge belongs to some matching. Okay? So there is a very easy algorithm and very naive algorithm to do that. You basically force this edge in the matching. Okay? So if we are looking at x, variable x, and value v, we are basically removing all the other possible value for variable x. So if w is a value, remove the edge. There is only one edge which is left for x. So for finding a maximum matching, x will be forced to take this value v. And then we look if we can, find a maximum matching whose values is essentially the number of variables. If we can do that, we are fine. Now, the problem with this, of course, is that we have to take all these edges and then find a maximum matching, take another edge, find another maximum matching. So it's really tiring. It takes a lot of time. Okay? So we can do better. And there is this basic property, crazy property by Birch in 1970, which was found by Jean-Charles Régin. And so what is interesting here is that this property seems to come out of nowhere. Okay, but I'm going to read it to you and tell you why it's relevant. Okay, basically this property is basically saying that an edge belongs to some, but not all. Okay, some, not all. Okay, matching. If given a maximum matching, it belongs to either two things. Okay, an even alternating cycle. Okay, so that's a cycle which has a length which is even. Okay, or an even alternating path which starts at a free vertex. Okay. So it's crazy, right? This property is crazy. First, we are looking at some but not all the matching, and then we have these two, crazy properties. But why is it so relevant to us? Well, the edges in the matching, we really don't care about them, right? Because we know that they are in the matching, so we know that we can remove them from the domain of the variables. So what we are really looking at here are edges which are not in the matching. So we know that in the best case, they belong to some matching, but they won't belong to all. And this is really what this property is about. So this is like magic, right? So this is just the property that we need. So the only thing that we have to do is for all these edges which are not in the matching, we have to look at two things. Do they belong to an even alternating cycle, or do they belong to an even alternating path which starts at the free vertex? Okay, so essentially this property is telling us really what we want to do. And it basically boils down to looking at these two things, okay, which is much easier essentially than looking at all the things that we had to do before. So what are the free vertices in this particular case? The free vertices are of, where are they? Are they the variables or the value? Well, we know that the constraint is feasible. So all the variables are matched. So the only free vertices are really the values. And that's where we're going to start, essentially, when we search for this even alternating path. Okay? So essentially what we're going to do is the same thing as for feasibility, except that it's the opposite. Okay? So we create a directed graph, but this time around, the edges are oriented in a different way. Why? Because before we were looking to assign the variables. Here we are going to look at alternating paths that are starting at the free vertices, and these guys are the values now. Okay? So we start at the bottom, and then we can go up if the edges don't belong to the matching, and edges belong to the matching go from top to the bottom. Okay? So this is, once again, an illustration. It's essentially the same thing as we have seen before, except that the edges are the other direction. So you see this guy here, this 7, this is a free variable. Okay, this is a free value. Okay, and then it can go up, to some of the variables, and then the edges in the matching, the blue edges are going from top to the bottom now. Okay, so remember we need to do a couple of things. We have to find the even alternating path. Okay, starting at the free vertex. We have only one free vertex in this particular case, and then we have to find the even alternating cycle. Okay, so we're going to do that. Okay, one step at a time. This is and using this graph. Okay, so the first thing we're going to do is to start for the even alternating path, starting from a free vertex P. Okay, so we have this beautiful 7 here. Okay, it's free. Okay, and then we are looking for an even alternating path. Okay, and we can take it as long as we can, because the longer it is, the more values we know cannot be removed. So in this particular case, we see this beautiful path. Chung, 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 chung. All these values here, we know that they belong to some, but not all the matching. Okay, great. Okay, so we can remove these. Well, we can make them dash, which basically means that please don't remove them. We know that they can't be removed. They belong to some matching. Okay, so that's the first step. Okay, and the second step now is going to be looking at things that belong to even alternating cycle. How do we do that? Well, there is this beautiful algorithm which is called finding strongly connected component, which does exactly that. These strongly connected components are basically components which can all reach move. There is a path to move from one to the other to all the other ones in the same connected component. So to do this now, the only thing that we have to do is to look this algorithm, okay, which was defined a long time ago using depth first search by Bob Tarjan. And then once you basically run this algorithm, you will find all the even alternating cycle. Okay, so in this particular case, look at this one. This is a beautiful alternating cycle. We start from x1, and then we go down, go to x2, go to x3, and go back to x1 afterwards. Okay, so essentially all these edges belong to an even alternating cycle. They belong to a strongly connected component. We can't touch these edges. They belong to some matching. Okay. And at this point, the only thing that is left are all the edges which belong to the original matching that we have found. Okay, those were the blue edges that we have seen before. And now everything else can be removed. Okay, so in this particular case, you see, okay, so this beautiful value 2, to x4 that we discussed at the beginning of the lecture, we know that we can remove it. Okay, and so you can remove all the edges which don't belong to the even alternating path, starting from a free vertex to the even alternating cycle, and then the matching. Okay, and so you can remove this x4 to 2, you can remove x5 to 3 and x5 to 4. And now essentially this is the prune graph after we have removed all the values that don't belong to any matching. Okay, so essentially the complexity here, once again, is going to be a nice low polynomial algorithm. You don't have to try all these particular edges and run a matching algorithm on them. It's much more efficient. Okay, and at this point, you know how to do feasibility and pruning for all different constraints. So what we have seen is this lecture are two things. We saw two different algorithms, okay, for finding feasibility and pruning of global constraints. One of them was a knapsack. We use a dynamic programming algorithm. The other one was an all-different constraint, which was basically using a matching algorithm, okay, and some graph algorithm for strongly connected components and finding paths. Okay, and that basically illustrates the whole purpose of global constraints. For every one of these constraints, we can use a dedicated algorithm exploiting the particular structure of that constraints. And the whole area of global constraints is just about that. Finding the best possible algorithm for feasibility and pruning, exploiting as much of the structure as we can. Okay, that's it for today. Thank you very much.